Hello. Today we're working on differentials. Now basically what a differential is actually has a lot of meanings, but today we're looking at it to find error. It's how we find errors. Now we talked about errors when we did tangent line approximations the other day, and these are very much related to them. Now to talk about a differential, the first thing we're going to do is look at what a function is. Now remember, the function is the curvy thing. There's my little function right here. And we're going to have a value at a. And it has a y value at f of a. The whole idea of a differential is to how can we approximate the value at b if we don't know it. We want to find f of b. So the whole idea today is to be how to approximate f of b. And that's what we're looking to do here. Now when we did tangent line approximation, what we did was we graphed the tangent line like so, and we approximated the value right here using the tangent line approximation. So the other question we're looking for is how accurate is our approximation. To do that, we're going to look at two different ways we can find error. Now the first one comes from the actual value. To give like an example of what we're going to talk about right now, let's say I want to find the square root of 26. I don't know what the square root of 26 is, but I do know the square root of 25. Same function, just a known value, is 5. So I can approximate the square root of 26 as by saying 5. This is what we call the difference in our function itself, because I'm using the function, the square root of x, to approximate the value. So values will come from the function. So if I were to kind of sketch out my original function here that I have, again, this is not the square root of x, and here's a, here's f of a, here's b, and here's f of b. The value, the error, or delta y and delta x, come from our slope formula, if you notice. So this is my delta x, and it's just b minus a. Right over here we have delta y. It's just the difference in my y values, f of b minus f of a. Now what I want you guys to notice is this. Like if this were my square root curve, this was my known value. Kind of like what we talked about when we did tangent line approximation. There's my known value. And I want to find how far off my actual answer is. So for something like this, how far off is my approximation? If I'm using 5, that's down here, how far off is it from my actual value? And there's the delta y. Now, we all know from experience that delta y over delta x is our slope. Now, if you notice, if I cross multiply, I get delta y equals m delta x. And this should look familiar to us. It's our tangent line equation. So to get error, we can just really look at our tangent line equation. Now that's the error from my actual values. Now when we did tangent line approximation, we get different types of errors. And we're going to take a look at those two right now. So, sorry about that. No focus. There we go. There. Okay, there we go. Sorry about that. Now, to get our tangent line approximation, instead of getting it from the function itself, we're going to look at our tangent line. Now, you may recall when we did tangent line approximation, when we draw our tangent line, we got our approximate here, and it was less of an error than our original error. So to get the error on our tangent line, the same idea, I draw my little triangle right here, but this becomes dx, and this is now dy because we're using tangent line, and tangent line involves the derivative dy dx. So to find dy, we're going to use our slope formula. We know dy dx equals f prime of x. So therefore dy equals f prime of x dx. And if you notice, the exact same formulas up here, but we're now using calculus terms. And also notice the error is going to be smaller. Remember, this is what we call the actual error in our estimation. So if we like estimate, it's the actual error. This right here is our approximate error. It's the error in our estimation from tangent lines. And if you notice, the tangent line estimation is a lot less than the actual error than itself. Now again, notice this is our tangent line. This is not tangent line. Sorry about that. This is y minus y1 equals my slope x minus x1, which we'll get to in just a few moments here. So let's go and turn over to the next page and kind of see how we can apply a lot of this. Okay. Right now. So let's say we're given the parabola f of x equals x squared, delta y, and we want to find delta y and dy. Now, so if I kind of sketch out this graph here, I want to find dy. Remember, this comes from the actual function, actual function f of x. So if I sketch it, my parabola, here's my value at 1. Okay? Now, I'm letting dx equal delta x equal 0.01. What that basically means is I go over 0.01 this way. So I'm at 1.01. And what I'm looking for is what is the actual change in my values. It's kind of, and we'll talk, so I'm looking for this distance right here, delta y, which is our f of y, or f of 1.01 minus f of 1. And if we type that in our calculator, this becomes 1.0201. This is just 1. And I get 0.0201. Now what this is saying, this is the error, ready? This is the error in our value, our y value, if we used x equals 1 to estimate f of 1.01. That's the difference in our y values. Now, what we're finding now is, now let's say we didn't use our actual error. Let's say we want to use tangent line. How accurate is calculus? So if I do the same thing in the first quadrant, we'll only work in the first quadrant. There's my known value. There's my tangent line. Same thing. Here's my 1.01, because remember, we're changing it by 0.01. I want to find dy. So to do this, I need my tangent line. So we're going to write our tangent line here. So to get our tangent line, we need a point. Well, we do have one known value, 1, 1. And we need the slope. Well, the slope comes from our derivative. That's just 2x. That comes from up here. X squared becomes 2x. So the slope at 1 becomes 2. So my tangent line becomes y minus 1 equals m x minus 1. Now, if you're really good, remember, this is dx, right? Well, this is just my change in y. So that's dy. My slope, we just said, was 2. And this is dx. The change in x, which we just said is 0.01. So my error now becomes 0.02. And if you notice, it is a lot smaller than my error up here. So this is my error if we use the tangent line. Now I can use this to find the actual error, but first, before we move on to that one, now let's say they ask me to find the y, the estimate. So if they ask me to find the estimate here, well, if they ask me to use to find the estimate, well, I can use my formula again. Change in y equals slope times change in x. I'm sorry, let me use this. dy equals slope times change in x. Well, my dy is just 1 minus 1. We know what that is. That's just my 0.02. So y is 1.02. So my estimate there would be 1.02. And that's my error. That's my estimate. That's how far off I could be. Now, let's take a look here. Find the error in the find the error. Now, that's what we did the day before. So to find the error, that's just take the actual value. Remember this, the actual minus your approximate. 0.0201 minus 0.02, and I get 0.0001. So 10 thousandths of a decimal off. Now let's take a look at some real world examples over here. Okay, ready? Now let's use differentials to approximate this value right here. We don't know what the cube root of 26.75 is, so we're going to use differentials to do so. And it's very easy to do. Now the first thing is we need to come up with an equation, and we're going to use the cube root of x since it's the cube root. I need a known value. Okay, I don't know the cube root of 26.75, but if I make that 26.75 is 27, I know its value is going to be 3. Next, it gives me my point. Next, I need the slope. Well, got to take the derivative. The derivative here is just 1 over 3 x to the 2/3. And if you plug in 27, we get 1 over 27. Coincidence only. Okay, so I can now write my tangent line. Y minus 3 equals 1 over square root of 27 x minus 27. And now I'm going to type that my x equals this 26.75. Y minus 3 equals, now I'm going to cheat a little bit, use a calculator here. Okay, and if I just type that in my calculator, I get, whoa, what's that become? Clear it out. 1 divided by 27 times 26.75 minus 27. I get, wow, negative 0.0093. And I can solve for y. So y becomes, so if I add 3 to that, I get, wow, look at that, 2.990741. I'll go a little bit further because watch what the actual value is. 26.75 to the 1/3. I get 9. Look at that. Look how accurate that is. 1, 2, 3, 4, up to 4 decimal places. That's how accurate our approximation is. Now, if we had just gone like a normal approximation, we probably would have guessed about the cube root of 27, which is 3, which is much further off than what our approximation, and that's what tangent lines do for us. All right, our next example down here, very simple, kind of cool way to write a tangent line, by the way. So it asked me to find dy. Well, it's telling me to take a derivative. So I got to take the derivative. dy dx, I get 15x squared. But I want to find dy dx. So I just multiply. Bring the dy dx over. I mean the dx over. I get 15x squared dx. And there it is. Now what's really cool about this one? What's awesome? Watch what we can do with this. This is going to be cool. You're going to like this. Okay? Now, notice, this is my tangent line right there. That's my tangent line. So let's say I had a point on this function, 1, 1. That's on that graph. If I write the tangent line, watch it change in y's. Y minus 1 equals 15x squared. Well, that's just my slope. 15 times 1 squared is 15. X minus 1. Look at that. Ta-da! Tangent line. Good job. All right, now, another cool application is from science. Let's say we got the radius of a ball bearing is 0.7 inches. And it has a possible error of 0.01 inches. Now, we want to use differentials to approximate. That's telling me to use a tangent line to approximate the following. The possible error in calculating the volume. Now, I need to use my volume, but I'm going to look at what I'm given first. Okay? It's telling me I'm given the radius is 0.7 inches. With the possible error in radius, now that's called dr, is plus or minus 0.01. Now that's my error in radius, it's just dr, okay? We'll talk about that in just a few moments. So I'm asked to find, oh my gosh, the error in volume, dv. Oh no, dv dr. So if I write out my volume formula, 4/3 pi r cubed, I take the derivative, not with respect to t, because it's not a related rate. I take the derivative with respect to r. I get dv dr, equals 4 pi r squared, and just that. Now, I'm looking for dv. See, so I keep them separate, dr and dv. If I multiply by dr now, I get 4 pi r squared dr. And notice, this is my tangent line. This is a tangent line. But I can just plug in. So dv becomes 4 pi, radius is 0.7 squared, multiply that by dr, plus or minus. Now, plus or minus because it can go either way. It can be as high as 0.70, 0.71 or as low as 0.69. So my change in volume, ready? If I type all that in my calculator, figure that out. 4 pi, I just type it in, 0.7 squared times 0.01, I get, is that right? 0.062, and that's going to be in inches cubed. So that's how much our error could be off. So an error of 0.01 inches here could give us an error of 0.062 cubic inches in our volume. Now next, the last thing we're going to look at is relative error, but let me go and get my light on here. There we go. Sorry about that. Lights go off if nobody moves. So relative error, we sometimes call that the percent error. And that's just going to be what the error is that you found over your actual value. Okay? So in other words, for us, it's dV over the actual volume. And if I write down my dV, I get plus or minus 0.062. Gotta get the volume, that's 4/3 pi, the radius is 0.7 cubed, and that's what goes here. And if I just type all that in, 4/3 times, what's that become? Pi, whoops, let me just do pi times 0.7 to the third, and I get 1.437. And I just divide that. 0.062 divided by 1.437, hit enter, and I get plus or minus 0.043, or about plus or minus 4.3%. And there is our error there. Alright, so take a look here, try them if you can. Okay, see you later. Bye-bye.